A particular trajectory of my research has become increasingly scorched over the last few years. Initially, this was born out of two things. Firstly, a frustration at field archaeologists casually pronouncing on whether shell was or was not burned based on inscrutable but certainly inconsistent criteria. And secondly, a fascination with uncommon accounts of the use of controlled fire in ethnographic shell working in disconnected places across the Pacific. Added to this was a further frustration with the conflation of heating and burning as processes in some experimental work. These various bugbears and intrigues led me to undertake some small-scale experiments, following procedures outlined in ethnographies, to reproduce shell artefacts using fire as a key part of the process. Following that, I supervised a PhD thesis which undertook a much larger set of experiments, which focused on mapping transformations in different types of shell using different degrees and durations of both heating and burning. These collective experiments led to a unique invitation to contribute to a large commissioned report for an Australian Aboriginal Land Council considering the likely impacts of increasingly common and increasingly intense bushfires, or wildfires more generally in global parlance, on Indigenous heritage. As the report is still being evaluated by the Council of Elders, I'll neither cite the report or the group in question. My contribution is also a very small component of a much larger body of work. Nevertheless, the act of undertaking this report section, which was specifically on the impacts of wildfires on archaeological shell, made me think about my pretty methodological experiments in a different way. As a rule, fire is one of the cardinal enemies of shell in taphonomic terms. So what would intense, increasingly regular wildfires mean for archaeological shell deposits? Did anything stand a chance of surviving? What? And in what fashion? There's been a fairly tenuous link in the global statements about climate change and increasingly widespread and intense wildfires or bushfires. To many scientists, there's clearly a link. However, scientists have been looking at the evidence really to try and demonstrate categorically this link. The most recent statement on this is in the IPCC Sixth Assessment Report, which is here in final draft form. And this is the statement in Chapter 1 as it relates to wildfires. Regional increases in area burned by wildfires up to double natural levels, tree mortality up to 20%, and biome shifts up to 20 kilometres latitudinally and 300 metres upslope have been attributed to anthropogenic climate change in tropical, temperate and boreal ecosystems around the world, stated with high confidence, damaging key aspects of ecological integrity. This degrades vegetation survival, habitat for biodiversity, water supplies, carbon sequestration, and other key aspects of the integrity of ecosystems and their ability to provide services for people, stated with high confidence. In Chapter 2 of the report, the authors go on to state that fire seasons have lengthened on 1/4 of vegetated area since 1979 as a result of increasing temperature, aridity, and drought, stated with medium confidence. Field evidence shows that anthropogenic climate change has increased the area burned by wildfire above natural levels in Western North America from 1984 to 17 by double for the Western USA and 11 times higher than natural in one extreme year in British Columbia, stated with high confidence. Burned area has increased in the Amazon, the Arctic, Australia, and parts of Africa and Asia, consistent with, but not formally attributed to, anthropogenic climate change. Wildfires generate up to 1/3 of global ecosystem carbon emissions, a feedback that exacerbates climate change, stated with high confidence. That's from the IPCC report, Chapter 2. As stressed by the IPCC, the extent of wildfire burning is increasing worldwide. Studies are increasingly demonstrating increased extent and increasing severity, as well as a longer fire season. Here are just two grabbed graphics from major reports and recent work. The link between climate change and the increasing nature and severity of bushfires in Australia is now beyond doubt, and the graphic presented there shows that even in the cool season there's a dramatic increase in wildfire occurrence. And you can clearly see the upward trend in the US as well, in the enhanced range when you look at the increases in area being burnt. Turning to archaeology, the occurrence of wild landscape fires in the past is something which should manifest in the archaeological record in at least some places at some times. But while we tend to think of landscape fires as natural events, large-scale burning as a cultural practice is widespread and has deep roots in many places. What's often referred to as fire stick farming is characteristic of Australian Indigenous cultural practice continent-wide. Culturally prescribed burning serves a great many parallel functions, reducing fuel load and thus severe natural fires, forcing regeneration, flushing out prey, and signalling presence to other groups on the landscape. In another manifestation of large-scale burning, we of course have swidden farming, also known as slash-and-burn agriculture. And this was, and indeed is in many places, common practice in a great many locations worldwide. For extant archaeological remains on the modern landscape, their ongoing preservation is increasingly threatened by wildfires, and larger, more frequent and more intense wildfires raise the stakes. There has been some thought given to this by heritage practitioners and agencies, with, from what I can see, the longest standing and most formalised thoughts being systematised in the US, particularly by the National Park Service. This involves not just assessing the preservation of materials after wildfires, but also surveying after burning to see if new sites have been revealed. When thinking about landscape burning in the past, or what it may mean for the future of material heritage, a solid understanding of the responses of key archaeological materials to burning is a prerequisite. For many materials, considerable research has already been done. For bone, there's numerous studies looking at responses to different fuel types, the presence or the variable presence of meat on a joint, the impact of fire on subsurface remains, all sorts of things. In terms of stone, the particular nature of thermal fracture and its diagnostic characteristics, spalling and potlid fractures, as well as colour changes brought on through thermal alteration. For ceramics and metal artefacts, fire is indeed inherent in the very process of their production and a key part of understanding them as materials. For shell, however, the research is incredibly patchy. While mineralogical transformations are acknowledged, shell is made from calcium carbonate in one of either two forms, aragonite or calcite, and aragonite is the less stable form, and over time and with particular contextual cues, aragonite will transform or recrystallize to calcite. One of the major catalysts for this transformation is high temperature and thus burning. And this transformation is well acknowledged in the literature, although the mechanics are patchily understood. And the tipping point for recrystallization via temperature or burning, what you'll often read in the literature is either incorrect or fairly obscure. It's not clear where the information is coming from. It seems to often rely on information from geology, which does not typically relate to what we know of as biogenic aragonite, as you have in mollusks, where an animal is actually producing the aragonite and laying it down. From my perspective, this patchiness and understanding of recrystallization and general responses of shell to fire and to thermal alteration wasn't so much an invitation to fill the gaps. I'm certainly no expert on, thermal kinetics, as it was to really sort out particular conundrums. While analysing some particularly Pleistocene assemblages, I'd noticed that burnt shell was preserved in far better condition, and probably outsurvived by some degree, non-burnt shell, and observations even during excavations, and we were relying on notebooks from the 1950s for the particular assemblage I'm thinking of. And the commentary about the general shell there was that it could be seen when they were excavating, but you couldn't pick it up, and it would crumble as soon as it was touched. And so what you've got as an extant assemblage now is the burnt shell that's heavily burnt, which has survived in diagnostic condition. On the flip side, at other sites I've worked on, burnt shell was only present in very disaggregated flakes and fragments, while the non-burnt shell was far better preserved. So what are the rules of thumb and generalisations? Only further research could really shed any light on that. As with other aspects of taphonomy, when it comes to shell, and indeed thinking about shell working, an understanding of fracture and disaggregation needs to use a consideration of microstructure as its starting point. Different types of shell have greater or lesser quantities of organics built into the matrix, and there's a variety of different sorts of matrices that we refer to as microstructures. This is where the individual crystals of aragonite or calcite are in different shapes, and then they're stacked and interwoven in different sorts of ways, typically using organic proteins as a sort of glue. Up on the slide here, I've got the major types that you'll find in different families of shells. The first, nacre, also known as mother of pearl, occurs in two different forms, in gastropods and bivalves. So in gastropods you get columnar nacre, which are these stacked tablets which are glued together in stacks, and then the stacks themselves are glued together. Sheet nacre is characteristic of bivalves, and that tends to be a little bit more lamellar. So as the stacks are building up, the crystals coalesce to form these sheets that lie parallel to the surface of the shell. B is crossed lamellar microstructure, which is present in a lot of the evolved gastropod and bivalve families, what people would tend to think of as clams or cockles, whelks, and so on. And here you've got these long lathes, and they're arranged at 45-degree angles to each other, roughly. So it has a very low proportion of organics, especially relative to, well, actually all of the other microstructures I'm showing on this diagram. You tend to get a very rough fracture with it. You can't cleave straight through because of the way it's put together. So it's a very robust, resilient microstructure. C is foliate microstructure, which is particularly characteristic of oysters, as in rock oysters. These are sort of thin arrow-shaped tablets that are set like shingles, really, like roof tiles, again glued together with organics. And D is prismatic. These again are stacked tablets of either aragonite or calcite. It depends on which shell is doing the building. It never occurs by itself. It always co-occurs with another form, usually nacre. So you'll get shells that have a nacreous mother of pearl interior, and the outside, more often than not, then is prismatic. It's very organic heavy, and if you whack it, it tends to come away in chunks. So the burning experiments that I undertook, along with different students at different points in time, really came from a base of starting with thinking about these microstructures and trying to understand the variation, and that indeed structured the whole methodological design. Other variables built into experiments included exposure to direct flames versus embers, versus heating in an oven, all completely different. The duration of exposure, of course, and the temperature. One of the first experiments, and one that was a catalyst really for formalising the studies, was trying to replicate a shell working procedure recounted by an anthropologist working in the highlands of New Guinea, and these were to make pearl shell crescents known as kina. And what they would do is that in order to break up the valve into the bit that they wanted, which was, they really had to get rid of the hinge, which is the bit I've got exposed there. It's often very thick, but the plane of fracture runs parallel to the shell, so it's not like you can flake it. It's very difficult to control fracture. It's very, very organic heavy. It tends to splinter, it tends to crack back into the shell. So I read about this particular method using fire and thought, okay, this is fascinating. And so we tried it out. So the bit of the pearl oyster that they wanted to retain was covered in mud, and then the whole thing was put into a hot fire. Off the top of my head, it was in there for 10 minutes or so, and then taken out. And you see the outside of the clay is baked. And when we took off the mud, it did indeed protect the shell that wasn't exposed. And the very thick hinge section, you could just literally crumble away with your fingers. It was completely disaggregated. And under low power microscope, as you see at the bottom, this was looking at that fractured surface after crumbling away the very burnt shell. You can see how lamellar that is, all of those different layers stacked one on top of the other. But one of the first responses, and you could actually hear it, was that the water within the shell structure, you could hear it bubbling, and it was steaming away. And I mean, potentially the organics were part of that as well, but you could see this bubbling on the surface, as you can see in the bottom right image, that was actually deforming the nacre. I think anyone who's worked with shell a lot and transformed shell a lot knows often what you see is not what you get, and things can be quite transformed, yet not appear so visually. And recrystallized shell is potentially very problematic for radiocarbon dating, for stable isotope analysis. So it's important to check using something beyond your two eyes to see whether shell has recrystallized or transformed in any way. And because of that, and given the controlled conditions, we thought, okay, well, let's take some samples for X-ray diffraction and have a look. And what we found was actually really intriguing. So the percentages that I've written up there are percentages aragonite. So mother of pearl is always constructed of the aragonite form of calcium carbonate. And under extreme circumstances and extreme heat, that should recrystallize to calcite. Now, the temperature measured in the fire that this was sitting in was over 600 degrees, which is over what any textbook would say recrystallization should happen. And yet, even in the most burnt portions, we've got aragonite at 97.5% of the total mineral content. So that really raised a lot of questions, and it was results like this that prompted more formalised studies that took place over the ensuing years. So the full set of systematic results, which was experiments over a range of different types of shells of all of the major microstructural types, looking at heating in an oven for different durations of time at different temperatures, as well as the indirect and direct burning in a fire, again different durations, different temperatures. This is all presented in the PhD thesis of Annette Oertli. And there are some publications which are, well, coming up to being in press at the moment. And she's also a co-author in the report to the Aboriginal Land Council I mentioned at the beginning. And her results, combined with other experiments which we ran in the lab, yielded, I guess, the following statements which could be made. Recrystallization rates across different types of shell under different conditions vary wildly, absolutely wildly. There's some shells, very robust, where you'll get a near total recrystallization after only 5 minutes, just sitting on hot coals, not even exposed to flames, while others, like the example I've just given you, retained most of their aragonitic structure after 10 minutes in direct flames at temperatures over 600 degrees Celsius. Fracture, delamination and disintegration patterns closely mapped onto microstructural types and the placement of organics within these structures. Thus, prismatic structures came away in blocky sections because prismatic structures are built in blocky sections, while naked delaminated prior to shearing. These are really exactly what you would expect. If you reduce the organics, you lose the glue. Metrics were noted to be impacted by burning, with shells sometimes reducing in overall size due to dehydration, and sometimes expanding in size due to delamination and the splitting apart of layers. Although the literature sometimes provides the following transformational pathway: aragonite transforms to calcite, transforms again to calcium oxide, we noted that this does not always happen. Differences in pathways were noticed when the same shell was modified via heating rather than via burning. Same temperature, 600 degrees in an oven versus 600 degrees on hot coals, you got quite different effects. And certainly in an oven, there wasn't a clear progression, always to the calcium oxide, to the most reduced phase. That's probably really poor chemistry terminology. Apologies to any chemists. And sometimes pyrogenic aragonite formed, and this is a really mercurial one in the literature because aragonite's known to not be particularly stable. It transforms to calcite. This is a truism. But the fact that you should get aragonite forming in a fire circumstance, which is what pyrogenic aragonite is something that's not fully understood in any branch of science. You get the formation of these tiny needles of aragonite, and it certainly noticed that in some of the experimental samples that she ran. Different shells, thermally altered in different ways, showed very diverse visual signatures of burning. Sometimes you got they were very white and powdery, which tends to indicate calcium oxide, sometimes black and very charred, sometimes with a yellowish tinge, sometimes with a greenish tinge. There was a huge variety of visual signatures. And the transformational pathways were specific to different types of shell. And it's worthy of note that white powdery shell more often than not, is produced by acid dissolution and weathering. If you see a white powdery shell, it's not typically a shell that's burnt and you're looking at calcium oxide. And blackened shell can be produced by microbial action. So this is to my field archaeologist friends who say, I've got a blackened shell and therefore it's burnt. It is in no way that simple. So thinking about all of these things in terms of a shell midden that might be sitting in the path of a bushfire, what to expect in terms of when a bushfire hits or a wildfire, what might be left behind, really sort of trying to apply the results of these experiments. I mean, it really did highlight how little we understand about shell and how much more systematization needs to be done in terms of our knowledge. But there were certainly take-home messages. I mean, shell is highly vulnerable to fire. We know this. Fire tends to be the enemy of shell. But the thresholds for and the nature of transformations are extremely variable. Take-home message 2 was that if shell survives, it's likely to be a biased assemblage. Some shell held up with reasonable structural integrity, and this is often the crossed lamellar shells, because of the way they're built, that they don't tend to just delaminate or come away in blocks. They're actually meshed together, and the organic fraction is so low in the overall structure. So we can expect them to outsurvive other types of shell, resulting in a biased assemblage. Additionally, if there's delaminated or fragmented shell, this will be more vulnerable to weathering afterwards. And given that high levels of erosion and sediment movement frequently occur after landscape burning, you can expect those fragmented shells to be extremely vulnerable. Take-home message 3. If you read a statement about transformational pathways and or thresholds, be very sceptical. Categorical statements about shell recrystallizing at XYZ temperature or particular responses. Variability was the order of the day. It's hugely diverse. Take-home message 4 was that buried remains may be afforded some protection from major fire damage, but they are likely to be transformed in some way. And that take-home message actually comes out of another set of experiments that were being run, and another PhD student who was looking at amino acid racemization and trying to look at it as a chronostratigraphic tool, not necessarily as a simple dating technique. But different amino acids racemize at different rates in the conditions when you have burning or sharply elevated temperatures. So what he was finding was that shell which you would look at and think, well, there's no evidence that that's burnt. If you looked at the ratios of aspartic to glutamic acid, you could clearly see that it had been exposed to fire. That was really interesting. So visually undiagnostic, not recrystallized, so mineralogically undiagnostic if you did X-ray diffraction, but the amino acids told us that it had been exposed to fire. So, I mean, over a number of years, there have been various largely informal actualistic taphonomic experiments, dominantly in the US, conducted in national parks, placing different types of material in the path of prescribed burns. And this is actually a really fruitful exercise and could be applied in a more widespread way to think about how material is responding in those very intense large-scale fires. It's one thing doing it in a campfire, but anyone who's been close to a bushfire or a wildfire knows that, well, it's quite a different experience, the wind and all of the conditions that go along with it. Finally, I mean, it's not all doom and gloom for archaeology, as wildfires can also reveal new archaeological resources, as post-fire surveys have repeatedly demonstrated. So fire is not necessarily the enemy, but as zooarchaeologists and archaeologists more generally, it is something that we certainly must strive to understand in the past, but also for the future. Thank you.